So in this section, we're moving away from just the characteristics of the exponential functions. Now we're going to actually look at creating the functions based off of real-world data. Just like we did in Unit 1 with trig functions, just like we did in Unit 7 with polynomial functions, now we're doing the same thing with exponential functions. So what we have in this table is the data for the year and the population of Canada according to the census. Now, yes, we do have 3 columns, but we're only going to pay attention to the year and this modified population of Canada, which has just been converted to millions, just to make things look a little bit nicer. Creating the model with the calculator has not changed. We will still go to the Stat menu. We will go to Edit. And just in the sake of saving a little bit of time on this video, I've gone ahead and I have pre-filled all of the data. Please feel free to pause the video now to put it in the calculator yourself. As always, it doesn't matter if you are using the app on the phone or the handheld calculator, the functionality will be the same. So once we get all of this data entered, we press second mode to quit out. We go back to the Stat menu. We go to the Calculations. And now we need to look for the type of function we are trying to create. These are exponential functions, which on my screen is option A, EXP-reg. You will be looking for the same thing on the handheld as well. So we're having that one. We'll press enter to calculate. And this is the function we get. The way the calculator writes it is y equals a times b. This symbol is called a caret. It is commonly referred to as a hat. It means exponent, so b to the exponent of x. Only because the calculator can't write things as superscript, it does that as a shorthand. So what we have here is a of 9.00, e minus 18. That is scientific notation. In reality, it is 9.00 times 10 to the power of negative 18. Again, because of the limitations of the display, that's how it's shown. B 1.022. So when we go to fill this into the equation, writing it with proper mathematical formatting, y equals 9.002 times 10 to the power of negative 18 times 1.022 to the power of x. Question B, assuming the population growth continued at the same rate, estimate the population in 2011. 2011 is the year, and the years are what we used for x. So we will be taking the equation and substituting in 2011 When we go to calculate this, it is possible to do it in one step. However, it's often better to do it in 2 steps because 1, we're dealing with scientific notation. 2, we're also dealing with exponents. So easiest thing, following BEDMAS, deal with the exponent first. 1.022 to the power of 2011 ends up being 1.013 times 10 to the power of 19. Multiplying those together gives us 91.22, and because we're dealing with the population in millions, 91.22 million. Now, anybody who knows anything about the population of Canada, population did not reach 91 million in 2011. In fact, it was closer to 35 million. So what that tells us is that the exponential equation did not remain true after we left the time period that was given to us. For this time period, the equation absolutely is true, but after that, the growth rate changed for whatever reasons, so it didn't prove true. If the equation had held true, then yes, Canada would have had a population of 91 million in 2011.